Hi there. This is JNEL, and this is Unit 1.1, Lesson 3 on wheel and axle. And excuse in this video if you hear a hiccuping noise because that's what I have right now, and that's annoying. So sorry about that if you hear that. So once again, this is Unit 1.1, Lesson 3, and handwriting's terrible, as usual. And then that is on wheel and axle. So here we go. So the wheel and axle, we know some examples of what a wheel and axle might be. You can think about what it might be. So let me just draw the first kind that there is. And this is just the type of drawing that is on the PLTW engineering formula sheet for, well, let's see. Well, actually, it's for all courses. So if you took IED, then you probably use that too. So if you look up the formula sheet, this is off of page 6, which is the last page. Yes. So right here, that's the wheel. I don't know if you can tell. It might just look like two backwards C's, but just imagine it as this is just half of it. So then this is the fulcrum, which is the base of the axle. And then if we do this, this is the resistance distance. And so that's the resistance distance. And then we have right here effort distance. Then we have right here effort force. And then we have right here, going this way, resistance force. So this is, oh, that's wrong. This would actually be the resistance force, and this is the effort force. Only for this type of wheel and axle, which this is axle driven, meaning that the axle is what makes the wheel move. That is the case for most, if not all, cars, because when you're turning it on and you're hitting gas, it all comes together to make the axle turn, which makes the wheels turn, and they turn faster based on how much speed you're going. So that's axle driven, and you can see why, because the effort is here at the base of the wheel, and the resistance force is this part of the tire that is rubbing on the road, because obviously if it's rubbing on the road, it's going to be it's a terrible drawing of a car, but it's going to be some resistance, and the effort is at the axle, really like at that side of the wheel, so because it's coming from the axle. So that is what it is for a axle driven. Now let's see a wheel driven one. So we doing the drawing again. This time the effort force is there. That's what I was attempting to draw first, but I couldn't do that. And then this time it's different, so still the fulcrum's here, but this time this length is the effort distance. Why isn't it doing anything? Effort distance. And then this segment, things messed up. Resistance distance. And so that is a wheel-driven one, because the wheel is what's making it happen. And if you can think of an example, an outside spigot. So, let's see, try to draw here. So this is the outside spigot, that's the water coming out of it. You personally have to turn that circle thing on the top to make it turn on, to make the water come out. So that's the effort force. And the resistance is basically what's keeping that thing on to where it doesn't just fly off like a frisbee. So that would be an example of a wheel-driven wheel and axle. Also a skateboard, because with the skateboard, you're not that it's you are making the effort by rubbing, like putting your foot on the ground and going back and forth to make it go. And the resistance is going to be what makes the wheels not just completely fall off. But it's not the axle that's moving it, because there's not a motor in a skateboard. So that's another example. So that's that. Now we can look at examples of problems maybe you'd see. Now let me see here. I'll pause for a second. Okay, so here we have a problem, and it might look a little bit messy. Okay, for one thing, I read that wrong, but that is, so we have the effort right here and the resistance force right there. So you can tell already that this is wheel driven. Then we have the effort distance and resistance distance. So let's say these are something that you'd have, some things you'd have to find. So I may, once again, that is dE over dR, which you can see that there are no values there yet. So I will add some real quick. So there we go. Now there's values. So these numbers may not be completely correct, but like that realistic, but they're just some that I came up with quick. So the DE effort distance is 7 feet, and then the DR is 2 feet. So 7 divided by 2 is 3.5, and so that would be the IMA. Not feet, though, because that cancels out. Now, lately I haven't had any examples that would require you to have your units, but if, let's say, you didn't have the value, a certain value, and it asked you for it, that's when you'd need it. Like if the D wasn't listed and it was like, find the D, then you would need to have feet. You could tell by the other distance that you would need that unit. But it's just 3.5 for that. Then the AMA is FR over FE, which would be 75 over 110, which is just going to be, that's 110, not 100. So that is 0.68 approximately, rounding to the hundredth. Then we circle that, and as you can see, that's less than 1 this time, because it requires a large effort force, as you can see, because it's 110 compared to the resistance force. So now the percent efficiency would, let's see what that is. So remember that if you remember the formula for that, sorry about that. I had to write down so that you wouldn't have to wait. But anyway, so it's AMA over IMA times 100. So that would be see, is there anything else we can do here? I'll just erase what's up here, which is taking a long time. Okay, I'll just try to remember that. AMA over IMA times 100. That's not 106, it's 100. And that turns out to be, okay, so that is approximately 0.19. You multiply that times 100, that is 19%, which means that is a terrible wheel and axle, because I said in another video, if it's less than 50%, then it's not good. And you could already tell before I even did it, that because that number is so small in the numerator, that would make it turn out to be small. Well, that is all for this video, so thank you for watching, and please see the playlist for the levers and other simple machine videos. Thank you.